Hi Chemistry 12-2 and welcome back. This is week 8, video 3. I was fooling myself to think I could put this all into one video. So with our second video chatted about families, alkenes and alkynes. And this video will be a short one, but we're going to talk about one other family, and it's the cyclic hydrocarbons. And a special case is called aromatics. So we'll take a look at aromatics. So again, our concentration is on nomenclature. We're learning how to name, very systematically, but how to name hydrocarbons and how to draw structural diagrams or interpret structural diagrams. Practice is the key. I've mentioned that in each video. I have posted under Files, week 8, 3 worksheets, and it's really important to do the practice. Check your work, make sure you're okay, ask questions if need be. This is the basis of organic chemistry, and if you're okay with this, you'll probably enjoy the topic a heck of a lot more and will be very successful with it. So practice, 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 then move to the assignment. And it's not a really long assignment. There's 4 parts, but they're short parts. So one part you'll be naming compounds, a mixture of hydrocarbons. One part you'll be drawing structural diagrams, again a mixture of hydrocarbon families. One section is on isomers, which is what we'll be talking about in this 4th video. And there's a few multiple choice I peppered in just for good measure. So, don't panic about having a really long assignment. The practice is what's key. So, right on to it. Cyclic or cyclic hydrocarbons. So rings. We know that hydrocarbons come in aliphatic or known as chains. And I'll just remind you here when we had this. So aliphatic, when we had our chains, so we've been looking at the aliphatic. So we've been looking at the alkanes, alkenes, and alkynes. All right, and talking about how they differ, single covalent bonds, double covalent bonds, at least one, triple covalent bonds, at least one. Now we're going to take a look at the other side of the T-chart. So we're going to take a look at cyclic. We'll look at alkanes that have rings, alkenes that have rings, alkynes that have rings. But there's a special case we want to talk about, and that's aromatics. So this is our plan for this video, this plan right here. Okay, so moving right along, promise I'm going to try and keep this one short. Moving right along, oops, I don't know what that is about. We'll just get rid of that. We are going to be looking at, find it again, cyclic hydrocarbons. So compounds that contain a hydrocarbon ring are called cyclic hydrocarbons. Rings with 5 or 6 carbons are the most abundant, but rings containing up to 20 carbons can be found in nature. So here's 4 examples of cyclic hydrocarbons. These are all alkanes. How do I know they're all alkanes? If you're saying because they have single covalent bonds between the carbons, Miss Ryan, you're absolutely right. And you'll see naming them, it's probably, again, so systematic, you probably guessed how we were going to name them. So this is prop because there's 3. It's ane because there's single bonds. And we put a cyclo in front because it's a ring, not a chain. Same thing here. Butane, right? 4 makes a square. So we have some specific drawings, and this is where I don't use the line format very often, but I do use the line format when I talk about rings. It just seems so much easier. Everywhere the line intersects, there's a carbon, and the H's are understood. And we'll talk about the number of H's in a minute. So here we have cyclopropane, cyclobutane, cyclopentane, and cyclohexane. Pentane, 5 carbons. Hexane, 6 carbons. Butane, 4 carbons. You can see each intersection of the line, you have a C and 2 H's. These are alkanes. And we name them just like the chain, except we've put a cyclo in front of them. They can have branches as well, and we'll take a look at some of those examples. Here is the line diagram, and you can see it's very, very clean and easy. You might have to practice with the shapes a little bit. Triangles mean 3, squares mean 4, pentagon kind of shaped like this, really not equal distance apart, but this is your 5, first base, or sorry, home plate I should say, and here's your 6, okay? So you have your 6-sided hex. cyclohexane. I wanted to remind you, every time you have an intersection, it's a carbon there, okay? These are alkanes, so each carbon has 2 other hydrogens with it. Boom. Any place you put, any place you have an intersection, you've got a carbon. And then we can have branches off of these. You've guessed it though, the family chain, the family chain will be the actual ring. So ring takes priority, okay? With single bonds, the branches took priority, and that's how we decided how to count our parent chain. In alkenes, we had a double bond, at least one, that took priority. That gets the lowest number. With alkynes, it's our triple bond, that takes the lowest number. And here with cyclos or cyclic, our ring is going to be the parent chain, and the things off of it will be branches, okay? And here's another way of illustrating, another way of illustrating the spatial diagram, so you can see the electron clouds in these diagrams here. So my question to you is, how the heck did we go from a chain to a ring? And so here I've just taken propane and I wrote it out so you could see the electrons. It's going to have to do with the electrons. And then we went from propane to cyclopropane. And if you count up the hydrogens, it's a little different. They look quite similar, right? So here we had 3 carbons. We have 3 carbons. They are bonded to each other. They are bonded to each other. Here, if you count up the H's, there's 6 H's. Here, if you count up the H's, there's 8. And I wanted to talk a little bit about general formulas and what has to happen to a chain in order for it to rearrange into a cyclopropane. It's the same thing that had to happen when we were looking at saturated versus unsaturated. Saturated, we're going to, remember, have the maximum amount of hydrogens, and we have single bonds. You would kind of guess that this is saturated, and in fact it actually is. Single bonds, and the carbons are holding as many H's as they can. So this classifies as a saturated hydrocarbon. When you have single bonds, the extra electrons that carbon have are bonded with hydrogens. Okay, so these are both saturated solution, or rather, sorry, saturated hydrocarbons. How did we change it into an unsaturated? If you're saying we had to remove some hydrogens, you're absolutely right. By removing hydrogens, we go from saturated to unsaturated. So when we wanted to make a double bond, we removed 2 H's to make that bond. So just to recap, if we take this H away, and we take this H away, it takes an electron as well, right? It only has 1 valence electron, but when it leaves the party, it takes the electron with it. Like my mom says, always leave with the one you came with. And so here we have 1 bond, but we've got these 2 free ones, and that's when we make that multiple bond. So by creating multiple bonds, we create unsaturated hydrocarbons, okay? If we wanted to go an extra step and take, and take this guy away, and I'm just recapping because we talked about that before, and take this guy away. So when you make multiple bonds, or when you go from saturated to unsaturated, it's all about taking away hydrogens. And that's going to be important next week when we start talking about organic reactions, okay? And when the hydrogen goes, it takes its electron with it. That frees up valence electrons for carbon, and then we can create a multiple bond, okay? And so we went from a single bond to a double bond to a triple bond. But there's sacrifice. We lose hydrogens when we do that, and this is a unsaturated solution. So that played into our general formulas. So when we found the general formula for alkanes, it was CnH2n plus 2. It was saturated, had as many H's as it could, plus 2 extras on the end. Alkenes, we took 2 hydrogens away to make that multiple bond. So we see that in the general formula. We take 2 hydrogens away. With alkenes, we had to take 2 more away. And so we see that in the general formula, 2n minus 2. So these guys will have less hydrogens because they have triple bonds, multiple bonds. Okay? So if I go back to my original, and I'll open those guys up, but this might be just as fast. So when I go back to my original, how am I going to keep single bonds but turn this chain into a ring. And I think you guys have probably figured it out by now. What happens when you have a chain, if you take an H away from one end of the chain and its electron, and you take an H away from the other end of the chain and its electron, we have a free electron here and a free electron here. And what they do is they get together, right? It's kind of hard to show this, but these two pairs share, and we create a chain turns into a ring. So this was a chain, but those two terminal carbons lost an H, and now they've turned into a ring. Okay? So I just wanted to take a minute to show that to you. So can you guess, right? Ring, chain. Chain, lose two hydrogens, boom, you have a ring. Chain, lose two hydrogens, boom. So butane can turn to cyclobutane if you take two H's off of those terminal carbons and join the chain together. So what would you guess? What do you think will be? It's one of these three. Which one would be best for cyclic hydrocarbons? How many H's did they lose? And if you're saying, Miss Ryan, they lost two, one from each end, and therefore the two ends were able to join, you're absolutely right, and they create that covalent bond. Okay, so alkenes and cyclic hydrocarbons have the same general formula, even though this guy has multiple bonds, this guy doesn't. This guy is unsaturated, this guy is saturated. Okay, just find that quite interesting. So let's practice before we get into aromatics. So here we have 4 molecules. Very easy to recognize as cyclic hydrocarbons because they got these rings, and the rings are the parent chain. So count the carbons in the rings, count the corners. So there's 4 carbons here. So we are working with I don't know if it's going to let me do this. Let's see. Maybe I'll move it down. Butane, because it's got single bonds, right? It's in a ring, so cyclo goes in front. We have a branch here. So if it was by itself, it's just cyclobutane. But we know the rules for branches. We need to know the size of the branch and where it is. The size of the branch is pretty easy. It's going to be 1 carbon. So we've got methyl, right? So we're kind of building from the back. But we have to let people know where that is. What's nice about a ring is there's no start or finish. So you get to choose which carbon is going to be number 1. And if you only have 1 branch, to give it the smallest number, that's the carbon it's going to start with. So I can start with any carbon here, but I choose to start with this carbon. So this carbon here, I don't know if this is still working, let's see. This is going to be 1, and you go counterclockwise. Yeah. No, clockwise, sorry. You go clockwise. Okay? So this ends up being my first carbon because I had a branch there. So I can just say methyl chlorobutane, that works. But if you want to be very, very precise, you can put the 1 there. Okay, if the number's left out, we assume it's on the first carbon. So we could have put that anywhere on any corner because that would have been our first carbon. Okay, hope that makes sense. Moving over here, we've got our chain, our ring. And we have 1, 2, 3, 4, 5. So right off the bat, I'll start here though as I pentane. They have single bonds, so we're good to go. We have to remember, this is what a lot of people forget, cyclo. Don't forget to put the cyclo in because that's going to give you the fact that the parent chain is a ring, not a chain. We have 2 branches. We have a methyl and we have a chloro. Okay, so which one do we want to give the number? It's going to be, if I start here, 1, 2, 3, 4, 5. If I start here, 1, 2, 3, 4, 5. So I think it's better to start here because it'll give me 1, 2, 3 as opposed to 1, 2, 3, 4. We go for the smallest combination. 1, 3 is better than 1, 4. Okay, so when we count, you pick where you want to start. You're in charge, but you've got to go clockwise after that. Okay, and it sticks. Once you decide to number it, it sticks. So we need to let people know that chloro is on the 1 and methyl. Which one should we write first? In the name, methyl comes first because And maybe I'll just join these together. Sorry, chloro comes first. So chloro, and you can put 1 in front of that if you want, or if you don't put a number there, it's understood as 1, okay? And I'm trying to write hyphen because it's between a letter and a number. 3 hyphen because it's between a letter and a number. Methyl, okay? And what we do is, here's our parent chain. I'm just going to move this maybe up here. This is our parent chain, so we put our branches right in front of it. Okay, 1-chloro, 3-methyl cyclopentane. If you take a quick look here, oh, we've got a multiple bond. No big deal, but count. 1, 2, 3, 4, 5, 6, 7. So I've got hep. What kind of a multiple bond do I have? I have a Y-N-E because it's a triple bond, but it's also a cycle or a ring. Okay, so cyclo goes in front. What takes priority? As in a chain, the multiple bond takes a priority. Okay, if there's no multiple bond, we look for our branches. If there's a multiple bond, it takes priority. It's always going to be between your 1 and your 2. So if this is 1, 2, 3, 4, 5, so 3 and 5 would be my branches. If this was 1, well, it couldn't be. It has to start, right? Because the multiple bond has to go between your 1 and your 2. So the counting here would be 1, 2, 3, 4, 5, 6, 7. Okay? The multiple bond gets the priority. You could say 1 if you wanted to, if you want to be fancy, right? Hyphen because it's between a number and a letter. Your branches, we have 3 and 5. They are bromos, but we have to say 3, comma, 5 because it's 2 numbers, hyphen. Let's move it up here so you can see it as it's building. And how do I let people know I have 2 bromos? And you're absolutely right, dibromo. Okay? And if we were going to put it right down here where it belongs, we're missing one thing, and that is your hyphen. So think about it. Obviously, I'm not here, looking over your shoulder, but those hyphens and commas are important. And over here, very quickly, before we move into our aromatics, you have 1, 2, 3, 4, 5, 6. So it's going to be hex. Oh, good Lord. See, I just looked at my time and I started racing, and this is what happens. So here we have, here, hex, ene, right? Hexene, because there's a double bond there, and people get so caught up in the double bond they forget to put the CYCLO in front of it, so don't forget that. I don't need a number here. I could put a number here, but I don't need a number here because it's going to be between the 1 and the 2, okay? And I could leave it just like that, or I could put 1 cyclohexane. So I hope that helps. All the rules are still true. We're just adding this ring now, so it's a little different. The word cyclo is the change. Wanted to mention a little bit about something called an aromatic compound. Okay, so you can read this. I don't have to read this to you. But an aromatic compound is called that because of its aroma. And a lot of the aromas we actually think of, these artificial, what am I trying to say? Artificial, I want to say seasoning, but that's not it. Flavoring. Some of the smells like vanilla, cinnamon, cloves, ginger, they're from actual chemical compounds, aromatic compounds. They are stable, they're unsaturated. Okay, so there's going to be some multiple bonds here, they're unsaturated, and they're cyclic, so that's why we talk about them here. The most common one is called benzene, so that's the one we're going to kind of concentrate on, is benzene. The electrons make up their bonds by are delocalized, and so can move around in an organized fashion. This is something we haven't seen before, so it's kind of a neat phenomenon. If you're a physicist, you've talked about resonance. Resonance is when we had our waves linking up so that we can increase the amplitude of our waves, okay? It means something a little different here. It actually means 2 isomers happening at the same time. And we haven't really talked about isomers yet. So let me try and explain to you what an aromatic looks like, okay, and what benzene is. And benzene's the only one we're going to worry about. So when you look at benzene, it's an aromatic 6-member carbon. So it's very similar to cyclohexane or cyclohexene, but it's a little different, and I'm going to tell you why. If you looked at this quickly, just from what we were doing earlier, you would notice that we have 1, 2, 3, 4, 5, 6. So we have a cyclo, right? Cyclohex, because there's 6. And we have multiple bonds here, and they're double bonds, so it's going to be ene. Technically, it would be 1, 3, 5 cyclohexatriene. That's what we would call it. 1, 3, 5 cyclohexatriene. And this would be 1, 3, 5 cyclohexatriene. But what you notice is, at any given time, these electrons are called delocalized, which means they don't stay put. These extra valence electrons travel around in a circle. And so at any given time, the multiple bond might be between these carbons, and these carbons. We kind of call them 1, 3, and 5. But at any other time, they might be between 2, 4, and 6. So this is that resonance we were talking about. When we have multiple bonds that move, when we have delocalized electrons, when the valence electrons move and you can't hammer down where the multiple bond is because it's always moving, we call that resonance. And here, these two molecules, at any given time, you might have this guy, you might have this guy, you might have this guy, you might have this guy. And so what they do is they merge the two isomers together. They merge the two molecules together, and what we get is something called benzene. And we have different symbols for it. Different textbooks use different symbols. This is my favorite symbol, so this is the symbol I'll use. Unfortunately, your textbook doesn't use it. But it actually draws a circle inside the cyclohexane because it's actually letting you know that the double bond is not always in one spot, that it's always moving around and around and around, and there's actually 3 of them rotating around and around and around, so I like that circle. Either the dotted line or the solid line, I like that circle. This one is confusing to me because it could also be, like I said, 1, 3, 5 cyclohexatriene, and you wouldn't know. So this to me is different to this. These would be representing benzene. And benzene is a special molecule. It's a cyclic molecule, but it's a special molecule because it really has a partner in crime. And at any given time, those chemical multiple bonds might be in different places. So it really creates unique chemical properties when that occurs. They actually work like they have single bonds. So even though they have 3 multiple bonds, they actually react like they have single bonds. They are unsaturated because each corner here has an H, and only one H, because the double bond is always moving. When we had single bonds, we had 2 H's at each corner. When we have multiple bonds, we have to take some of those H's away. But because these multiple bonds are moving all the time, each of these corners keep an H. And so it's a very unique molecule. It's the only aromatic we'll talk about, but it really creates unique chemical properties, especially smelly odor properties. And we're going to learn how to name it, okay? All right, so how are we going to name this? So when it's by itself, and I'm just going to put a circle in here because that's really what you're going to see for me. I just took these pictures out of your textbook. But for me, to show that this is benzene, you'll see a circle in there, okay? You'll see a circle in there. You'll see a circle in there. And that's going to let you know that we're talking about benzene. Substituted aromatic compounds. So benzene can be a family, right? It can be your family chain. It can be your boss. It can be the main part of the compound, or it can be a branch. So I want to show you 3 scenarios where we have benzene. So here we have benzene, and what's nice about it is it's like Cher. It has one name. It's like pink, right? It's I'm trying to think of someone else that has one name. Can't think of anyone right now. So Because here it's the parent chain, we call it benzene. And because there's one branch, we call it methylbenzene. Again, methylbenzene is the IUPAC name. Toluene is the traditional name. We're not going to worry about traditional names. So benzene is the family. You see the circle there. And methyl is the branch. Again, we get to choose where we count, so branch goes. And you might say, what about the double bonds? Aren't they priority? No, the ring takes up that circle in the center, takes up or represents the multiple bonds. So the fact that benzene is the parent chain is enough. Our branch can be named at the first carbon. Over here, the same thing. We have benzene, but our branch this time is ethyl. So ethylbenzene. Again, we can say we leave out the number, or we could put 1 there because it's at the top. This is a little different. Here you can see you've got your parent chain, and then you have this phenol. And a lot of people are like, well, how do you know which one's the parent chain? Can't this be a branch on the benzene? And the answer is no, because this branch here, you wouldn't have a branch that has like 2 carbons on one side and 4 carbons on the other side. You'd have to have the branch on the end, right? So that gives me a big hint that this is actually the branch. This is your parent chain. So 1, 2, 3, 4, 5, 6. So hexane, single bond, so it's A and E. So we have hexane, right? But on the 3rd carbon, if we count this way, because we want to give it its smallest number, 1, 2, 3. If we counted this way, it would have been on the 4. So 1, 2, 3. On the 3rd carbon, there's a benzene. But when benzene is a branch, okay, it's phenyl. Still the YL because it's a branch, but we use the term phenyl, okay? So phenyl is when benzene acts as a branch. It's called benzene when it's the parent chain, and it has branches off of it, okay? And 3 minutes to spare. I don't think we have to get into this. This is just, again, going back to traditional naming about ortho, meta, and para. That's all about where the branches are. So here you see you have branches 1 and 2. Here you have branches 1 and 3. Here you have branches 1 and 4. You wouldn't have 1 and 5 because that would turn into 1 and 3. We just count the other way. So depending on where those methyl branches are, the older way of naming them would have called them ortho, meta, or para. Okay, so ortho is when they're 1 and 2. Meta is when they're 1 and 3. And when they're 1 and 4, you have P or para. But you don't have to worry about that. I just want to show you benzene. So I would call this 1,2-dimethylbenzene, 1,3-dimethylbenzene, 1,4-dimethylbenzene, and I would put in a circle here instead of those multiple bonds. And there's just a really neat characteristics that come along with benzene. So I hope that helps. So now you are set. We have looked at all the hydrocarbon families we're going to look at. My last video is on isomers, but it doesn't have to do with naming compounds. So work on those practice sheets. Make sure you're A-OK. Have lots of questions for Tuesday, and then you can start looking at that assignment. Hope this helps. Take care.